All right, welcome back. In this video, we're going to be discussing how to design beams using the AISC tables for compact shapes. If you remember from our previous talks, we've talked about the relationship between the unbraced length of a beam and the nominal moment capacity. In particular, these tables are used to help us evaluate the lateral torsional buckling criteria for a given beam. Okay, and the general curve that we have, this general relationship, is set up something that kind of looks like this. All right, and so what we have is we have the unbraced length. This is the distance between the bracing points on a beam, and I'll explain that here in a little bit. And the nominal moment capacity. You can see that there are three distinct regions. All right, the nominal moment capacity is in region 1, maxes out at the plastic moment, this V and P value. Okay, and then there's a linear interpolation equation that occurs in region 2 where it reduces down to this VMR value. Okay, and then out here in region 3 becomes a slender element, and this just tapers off as the length goes out to infinity on there. Okay, now to use the AISC tables, they have taken this curve and they have broken it down into a couple of different setups. All right, so I'm going to show you one of them in this particular case, and then in particular, we're looking at table 3-10. All right, and so this is the upper part of it, and you can see that it's kind of hard to see, but if I can zoom this in a little bit, maybe we can see a little bit more. Okay, almost make the values out, but hopefully you have the manual along with you, but we can kind of at least explain the process for what you have happening. Now in this curve, okay, all of these tables in 310, you can see as I flip through to the next page, it's just more and more of the same curves and the same lines and so forth and so on. Okay, now something interesting happens if you start to look at the general shape. So okay, every line in this table is a different shape. Okay, and you'll see that some lines are dashed and some lines are solid, and there are solid dots, and there's some circular dots that I'll show you on there. But in general, every one of these is that same curve that I just showed you. This curve right here is located in this table for every shape that's in the manual. Okay, and so you can see, in this particular case, and it's this top particular value up here, this W12 by 53. Okay, you can see that there's a flat region here. Okay, and then it slopes down. So the region 1 is that flat portion that we saw, and then this solid sloped line here, it starts at this solid dot. That's your LP value. Okay, and if you look down at the bottom of the table, you can see that what they're plotting then is they're plotting the nominal moment capacity up this axis, and I'm plotting the unbraced length here. All right, and so what happens is that solid line, if I were to follow it down, would come down, and he would have an LB value of about 5 feet, the LP right here. Okay, again, my fingers are doing a great job of pointing it out, but you guys get the idea. Okay, and then if you look on some of the other pages, see if we can find one for you. It's kind of hard to see, but on the page right before this, you can see that there's a little small circle right there. Okay, and that's the LR value for that particular curve. Okay, now this is on page 3-118 if you're playing along at home. Okay, but that's in general, this LB versus VMN curve are plotted for you for all of the shapes in the section. So now it's just a matter of being able to figure out, well, where are we at on these curves and how do I use these tables to be able to define our particular sections. All right, so the basic premise is this. Okay, and I wrote this out for you just so if you want to pause the video, make a note, you can kind of play along at home. All right, as we talked about in the curves here, right? Okay, again, this is the MN up here up this vertical axis. If I pull this down, we'll talk a little bit about these tables. Okay, and then LB we said was across the bottom. All right, a couple of things to point out. The tables are calibrated for 50 KSI, as up here, and a specific CB value of 1.0. Okay, this is the worst case CB value for a beam in flexure. Okay, 1.0 means that the moment's being applied constantly along the entire section, and there's no relief due to light loading a part of the beam versus on others within a particular span. So this becomes a bit of a challenge. Now, conservatively, if I just use these tables straight away, I could come in and plot my values, and I could pull off a shape on this, and we would just be good to go. But it's not the most efficient use of the section, and you'll end up over designing a beam as a result of that. Okay, so I'm going to show you how to correct those as well. Okay, so all we're going to do in this, okay, in these particular curves, oops, get my page set here so we can get back to it. okay, is something that looks like this, all right? We're going to plot what we call this M 1.0 value. So now this isn't an official AISC term or anything, but what this is the equivalent CB value as if CB were 1.0. Okay, and so that becomes this vertical axis on that curve that I just showed you. Okay, and then on the bottom of this thing would be the unbraced length that we're looking for, the span that we're looking at. Okay, and so to calculate the equivalent moment for CB of 1.0, I take the actual moment in the span that I'm looking at, or the section of the beam that I'm looking at, and I divide it by the corresponding CB value for that. And that will basically scales it down to 1.0, and then I can use that value to come into the tables to make my selection. All right, so all you're going to do is you're going to do this computation, calculate 1.0, okay, and I'm going to plot that guy versus the equivalent LB value, the equivalent unbraced length, if you will. Okay, and so if this is LB, and this was my endpoint 1.0, there's a point on those plots that look something like this. Now, I've kind of reproduced, sort of, the way that table looked, okay? There were lines that were dotted, there were lines that were solid, and the ones that we're worried about are the solid lines. So from this point, all I have to do to choose the shape that is sufficient for that M 1.0 value at that particular LB is I go take off out of this point and I move up as I go. Now, if the first line that I come to, if it's a dash line, I keep going. And I keep going and going and going and across all the dash lines, I mean, there could be 30 of these things in the way, I guess. That might be an exaggeration, but we keep increasing until I get to that first solid line. It turns out that first solid line is the lightest shape that will carry the load that we want at that particular unbraced length in that particular section. All right, that's it. That's all there is to it, to being able to choose this thing. Okay, so it's no problem. Now, there are some other considerations that we have to kind of take a look at. Okay, remember that because of the way this curve is shaped, if I'm multiplying by that CB value, I could end up, at a value that's actually significantly higher than what the initial MP value is capable of carrying. This is the actual maximum that any particular section can carry. We can't ever go higher than this. Okay, so we've got to kind of keep our eyes on that maximum value as well. Okay, all right, so now I've got an example. I'm going to show you how to work this thing, and we'll see some interesting details that start to come out of this, I hope. Okay, all right, so if you remember from our last video, we had a beam that was set up such that it was simply supported. I had a point load in the middle of 51.8 kips and a distributed load of 1.44 kips. That'd be KLF. I can get our units on there, okay? And we're going to assume, unlike the last video where we did it for 36 KSI, we're now doing it for 50. Okay, so 50 KSI says, hey, I can use the tables. 50 KSI generally in the AISC manual is good news because it means there's generally a table for everything if you just know how to use it, okay? So we're going to redo this example in 50 KSI and kind of go from there. So all I've done in this is I've done the statics, down the reactions, 49 kips each, okay? The span of the beam is 30 feet, okay? And I haven't talked anything about the bracing yet because that's going to change as we start to do our calculations, okay? And then the moment diagram for this we found last time was to be 562 kip feet, all right? And so the way that we have to do this, the biggest challenge in these non-standard sections is, remember in table 3.1 we had CB values tabulated for us for point loads at the middle of simply supported beams and several different cases, but I never had a specific case that was a point load and a distributed case together at the same time. So that's where we got to kind of come in and go back to our basic statics and be able to do some generalized equation kind of calculations to figure out what are the points that correspond to those particular values. So all I'm going to do is I'm going to run through real quick and calculate the generalized moment equation. Okay, so we know that, to define this moment curve, there are actually two different equations that have to happen. Okay, this looks like a parabola. It actually comes up to a point. Okay, so it's a disc. The slope is not continuous from one side to the other at that particular location. So we've got to break this up into pieces. So all I'm going to do is I'm going to draw a free body diagram. The first one is for a cut that takes place somewhere in that first 15 feet. All right. So I've got, my reaction, my distributed load, and these are the revealed internal forces that show up when I do that. Okay, I'm going to call this as some arbitrary dimension x. So whether I cut it at x equals 1 feet, or I cut it at 5 feet, or I cut it all the way up to 14.99 feet, this picture never changes. Okay, and so we have 0 less than x less than 15 feet. That's the region that we're dealing with. That's my region 1 that I called out here. Okay, and when I do that, I can write the basic statics equations for the moment, because that's what we need to be able to calculate the values that are needed for CB. And I can write the equation like something like this. All right, so I'm going to take the distributed load multiplied by x. That gives me the value of the total load, and then its location is at the middle, so that's why it's times x over 2. And then I'm going to subtract off the moment countered by AY at a distance of X. So again, we're summing moments at this location right there. Okay, plus the applied moment at M at the cut in, and then of course V is times 0, so I didn't even write that in the equation. Just basic statics. You guys can do this. Okay, all right, so once I do that, the equation is AYX minus WX squared over 2, and if I plug in our values for this example, I get an equation that looks like this, 49x minus 0.77x squared, and that's valid on the interval 0 less than x less than 15. Okay, doing the same thing, if I go to the next region, okay, now we're looking at 15 feet less than or equal to x less than 30 feet, okay? So that's the span that's over here on the second side of this thing, okay? Now, you notice the free body diagram changes a little because now I've moved the cut line past the point load and this point load starts to show up, okay? So all we have to do is basically include him in our calculations and repeat the process. Okay, so if I do that on here, you get an equation of something like this. Again, WX squared over 2 minus AY over X. Plus now I get that PU times X minus 15 because it's X from here to here, and then it's 15 feet from here to here. Okay, so the distance that I'm taking from, again, I'm summing at the same point at the cut, is X minus 15, all right? And so those are our generalized equations. So, and you can do this for, any number of regions, any number of point loads, and so forth and so on. But that's kind of your quick statics review, if you will, on those. Okay, all right, so here we go. All right, so now let's consider, the effects of bracing on this thing specifically, okay? So the first example that we're going to look at is we're going to look at a case where I decide that I'm going to brace this beam at the ends and at the midpoint. Okay, the span of this thing is 30 feet, so normally there will be at least one set of bracing. It probably should be more than that, but a 30-foot long beam is highly inefficient for most standard W shapes under most standard loads. Okay, now some facts that we know, we're going to take advantage of a little bit of symmetry. Okay, note that for our example, our moment diagram is the loading was symmetric, which made the moment diagram symmetric. So when I go through, technically I have to consider this span and I have to consider this one as two different designs. Okay, now I want to make this the same beam for both, so I would have to make sure that it works for both of these particular design cases. But because of symmetry, I know that this guy and this guy are exactly the same. Okay, so we can go through and we can start to calculate our moments accordingly. So if you remember, when we calculate CB, I had to look at the quarter points, right? We had that basic big equation that looks something kind of like this. 12.5 in max over 2.5, that's a 2.5. Okay, 0.5 in max plus 3 MA plus 4 MB plus 3 MC. That's the equation that we talked about last time. Okay, and so basically, remember, A, B, and C all correspond to the quarter points that exist between a set of bracing. All right, so if I drew this out correctly, okay, here's my first span. That's my LB1, if you will. Okay, my LB1 is 15 feet. That's the distance between these 2 points. And then my A1 is at 1/4 of that distance. B1 is at 1/2 of that distance. And C1 is at 3/4 of the distance. Okay, and again, I'm measuring X as 0 at the left, 15 in the middle, and 30 at the right. Okay, so, and again, this thing is symmetric. So if I do that, whatever we find here will be the same for the next one over. All right, so all I have to do now is go in and use my generalized equations for this. Okay, and notice that, okay, well, my A1 coordinate is located at X equals 3.75 feet, right? That's the quarter point of 15. All right, and if I do that and I plug into my moment equation, I get 173 kip feet. And do the same thing for B1. B1 is at the middle, that's 7.5 feet. Okay, and then MB1 then is 324 kip feet. Again, just plugging and chugging. And you can check my math, pause the video and do the calculations yourself if you need the practice. C1 then is located at X equals 11.25 feet, and then so MC1 is 463. And then remember, we also need the maximum moment within that span. And from this picture, within this bracing point, you can see that the maximum is actually at the end, okay? And that was that 562 number that we had last time, okay? So that's why Mmax is here. So if I plug all those in, and I shake them into my formula, okay, and we plug into our calculations, then we find out that the CB for that first region is actually 1.52. Okay, so it's it's fairly generous for us. Okay, so all we have to do then to choose this beam is we have to come in and we have to look at calculating what is that M1.0. This is the table input value. All right, so I'm going to take my maximum moment because I still have to design for this guy. He's the worst in the entire span, so we're going to clearly design for him. Okay, but then I'm going to divide it by my CB value. So I'm going to take my 562 and I'm going to divide it by my 1.52, and that's going to give me a design moment in my table as 370 kip feet. All right, so what we're going to do is we're now going to jump into our table. Okay, and I'll kind of show you how we do this. Get myself situated here. If you're playing along at home, this is the table 310. Okay, and we are looking at 3.117. Okay, all right, so if I can get this in. So all we're going to do is we're going to read out my LB was 15 feet. So we're coming up here. If you kind of lay the straight edge on here, right there, I'm going to read all the way up until I find my moment, which was, what was the value? It was 370. Okay, and that's taking my page off. Over here. All right, so 370. All right, so if I look, sorry, I was on the wrong page. We're on, yeah, 3117. That's what I said. Okay, I was on the wrong page, so make sure you get the right one. So again, we're going to come in here. I'm going to come in at 15 feet, and I'm going to read up until I find my 370 number, which would occur somewhere right about here. Okay, so if I take that point, so my 370 was sitting about this location, and I'm coming over. It's this point that's right there. Sorry about that. Come in, so my 370 ends up being at the 15, ends up being at right about this location here. All right, so what we do then is from that point right there, I read vertically along this same line. So we're still following the edge of this straight edge, and I'm coming up until I get to the first solid line. You can see right here, I cross a couple of dash lines, okay, but then there's this solid guy that's right here, and if you look over there, that size is a 21 by 62, so that would be my first guess on here, okay? And so we're going to pull that one, and we're going to kind of evaluate, is that one sufficient for what we're trying to do? All right, and so that's where the size of 21 by 62 came from, all right? Okay, so at that location, I know it was kind of hard to see in the graph, but I just want to kind of show the mechanics of it. We found out that the moment on the CB 1.0 table was 387. Okay, but the nominal moment capacity we know is CB times that value. All right, and so according to that calculation, we would say it would be 1.52 times 387 would be an equivalent of 588. Okay, and that's well above our 562. Okay, so we would think, oh, hey, we're in business, but remember that we're capped on the size by the plastic moment value. We can't ever exceed that limit. It's a hard limit. All right, so if we do that, okay, I'll go in and I'll show you. We can go back to our ZX tables, and we kind of use 310 and 32 together. All right. Okay, and so if we come in, here's our 32, and my 21 by 62 shape is this guy right here. Okay, and if I read across on this thing, again, we're looking at a 50 KSI table. We're doing the ZX because we're bending about the primary direction. So make sure you're getting the right tables, okay? And I'm going to read across on this thing until I find what would be my phi and p value. And you'll notice that value says 540. So that's the actual limit on what this guy can take, this W21 by 62. Okay, and that's a problem, right? Because the phi and p value on this is 540, okay? But that's less than my 562 maximum value, so this beam is technically no good. It looked like it was when we did the first set of calculations and scaled the table, but it's actually exceeding the actual plastic limit, so it's not a good selection. All right, so we need to go through and we need to modify our guess a little bit. All right, so because our last selection didn't work, we have to choose another size. And so we can go back to our page 3-117. Okay, and we were sitting at our 15, and we were sitting on top of this 21 by 62 that was sitting right about here. Okay, and so all we do now is just basically continue reading up. Okay, and so our next solid line above us here is the 16 by 67 guy that's sitting at about 423 kip feet. Okay, now I'm going to make a note of the next one, which is the 21 by 68 also, that's sitting up here at about 438 or something like that. We'll make a note of him, okay, because I'm going to show you something on those other pages that we had. Okay, so if we go back to 3.2, okay, the first guess that we had was our 16 by 67, right? So 423, CB of 1, play the same game, CB is 1.52, The PMP then 1.52. Put a dot on that guy, times 423 is 643, more than enough, okay? It's the NP value that we need to double check, okay? And if we go and look for our 67, remember we were sitting up here at 21 by 62. The 16 by 67 is actually this guy down here, okay? And if I read across, clearly the NP value is even smaller than it was before, so he's not good enough, okay? So what we do is we go back to the table and I read up to the next solid line, which would have been that 21 by 68. Okay, and so my 21 by 68 value then is the guy that's sitting over here on the next page, right? And so his NP value is 600. We're more than sufficient for what it is that we're trying to do, okay? All right, so if we go back, that's kind of what we did on the rest of the test, trying to eliminate flipping back and forth. Okay, so 16 by 67, PMP is 495, it's still no good. Okay, so then we go to the next solid line, which gives us our W21 by 68, VMN is 438 at CB 1.0, okay, increasing, multiplying by our 1.52 gets us 666 kip feet, okay, and so for the VMP value for this guy, 21 by 68, the VMP would also be 600, okay, which is what we just showed you in the tables, okay. That guy is so our nominal moment on this thing is the smaller of those two values again, 666 or 600, so we choose the 600, that's our smallest, okay, and so the nominal capacity of this beam at an unbraced length of 15 feet is 600, that's greater than the 562, which was our M max, okay, M max for us there, so we're okay, and so our final selection for this particular beam would be a W21 by 68 by 30 feet long of 50 KSI steel. I just said A992, it could be anything. Okay, braced at the ends as well as the midspan both, and that will get us our size on him. Okay, all right, now, what do we do if we change the bracing pattern? Okay, and so if we look at it, consider the same example, and we'll go through this fairly quickly. I've worked out a lot of the values for you. If we brace it at the quarter points instead, okay, so before I did it at the ends, I did it at the middle, and now I'm going to brace it at the quarter points. What changes, and what do we have to do differently? Well, now you notice that we have 4 regions that we have to consider. Now again, we're going to take advantage of symmetry because this side over here is the same as the side that we have over here. All right, so I have 2 regions that we have to consider, okay? And remember, everything that we do in the design of these compact shapes, these LB problems, unbraced length problems on there, is I have to consider the unbraced length between each of the spans. In this case, they're both the same, 7.5 and 7.5. That doesn't have to be the case. I could have different spans on here, in which case this check becomes even more important. Okay, but for us, we're the same. So LB1 is 7.5, LB2 is 7.5. Okay, and then what I have to do is I have to figure out the CB value for each one of these because the moment diagram is doing something different in this span than it is in this span. Okay. All right, so we've got a design for all of the bracing spans. All right, so if I run through the numbers real quick, I'll save us some of the calculations. All right, for region 1, that was this first, pull it down a little bit further. That was that first span here. Okay, my X dimensions are now a lot smaller. Okay, my unbraced length is 7.5, so my quarter points are 1.8, 3.7, and 5.6. And the corresponding moments are 90, 173, 251, and 324. And if I plug those into the CB formula, you find out CB is 1.6. Okay, do the same thing for region 2, plugging in different X values. Now X is 9.3, 11.25, 13.12, and the max is at 15. Okay, and your moments are 390, 454, 510, and 562. If I plug those into the CB equation, you can see that the CB is actually 1.2. It's actually somewhat even less, okay? And it's these smaller CB values that that are generally the most severe. But again, we don't know. So what we have to do is we now have to kind of repeat our process for our design cases, okay? And I would have to consider the case for region 1 in which the maximum moment was only 324, the unbraced length was 7.5 feet, and our CB1 value was 1.6. These 3 guys together make the set of criteria that we have to look up, okay? And then region 2 would be Nmax of 562, that was the peak moment, our LB2 of 7.5, and our CB2 of 1.2. And we would have to go through and play this exact same game, and I would have to choose a beam that worked for both cases, okay? So you kind of do what we did to choose the beam size for one of them, and normally I start with the higher moment and the smaller CB value. If that's the case, this guy clearly controls, okay? But if I don't know which one, sometimes, you know, maybe this span's a lot longer, you know, and you don't know which one's going to control. Choose one and then check the other as we start to have to look at this, okay? So just make sure that you're always checking all 3 of these things, and it's the exact same process. I need a moment, which I would convert to my M1 value, LB2 and CB2, and then do the same thing, find an M1 value for this one, for your unbraced length, and then you basically go through and repeat the process. Okay, so that's kind of the basics of what it is that we're looking at, what we're looking to try to do. Okay, all right. So at this point, we'll go ahead and stop there. Hopefully this is kind of explaining how the AISC tables work. You'll notice that those figures are really, really handy, but you got to be careful about exceeding that maximum value, or that MP, because our LB value is always bounded by MP on the upper end. So make sure that you're checking for that. Okay, I hope this has kind of helped clarify how the AISC tables work. Apologize for the break in the middle. We needed to check a number, and we'll be good to go. Hopefully this has helped. Stay tuned for more in the world of beams, okay, after this. Thank you.